Hello students, welcome back. Previously, we went through this example problem using French notation, x prime and y prime. Now let's do a little bit harder problem, this one. And this time we are going to use German notation, dx dt and dy dt. The key to this kind of problem is to take the derivative implicitly. We have one equation here, original, and the implicit differentiation will give you the second equation. Another equation with some derivatives involved. So we have two equations and four unknown variables, xy, and also dx dt and dy dt. Among those, two of them are given. So we have only two unknown variables. With two equations, we can handle it. Okay, here we go. First, the implicit differentiation. Let's see, how does it work? Take the derivative, so 2 comes out as coefficient, and subtract 1 from the power. Nothing changes inside. And we have to multiply the derivative of the inside, right? And of course, in the right-hand side, we're going to get something. By the way, 2 minus 1 is just 1, and you don't write 1 power. So you can write like this. And then what's the derivative of the inside? Well, the derivative of y squared is 2y, but dy dt pops out. And the derivative of x squared is 2x, but dx dt. And derivative of 3x is 3, but we have dx dt. Okay, that completes the left-hand side. Outer function, inside stays the same, and the derivative of the inside, the typical chain rule problem. Now let's go to the right-hand side. Derivative of 4 minus this product function. Now the derivative of 4 is, well, that's constant, so always that's 0. And then the product. The derivative of the first function times the second function plus first function times the derivative of the second function. Is that it? No, not really. Close but no cigar. We took the derivative by x, and therefore dx dt pop out. Here I took the derivative by y, so we have dy dt. That'll complete the problem. What did I do here? Yes, this and that. Okay, that's the same, so let's just keep it like this. And then let's put in numbers. Let's put in numbers. So over here, let's put in x equals to -1, so -1 goes here. And then -1 goes here. And then -1 goes here. -1 goes here. Another -1. Oh, so many of those. Did I plug in all the x values now? Please check. If necessary, stop the playback. Now how about dx dt? Okay, that's 2. That's 2. And then that's 2. All good? Okay, so from here, plug in x equal to -1, we get this. From here, we plug in x equal to -1, and dx dt is 2, we get these. what did I do here? Yeah, very same. So no need for these. Now, can I close these? The original and the implicit differentiation. And now, after plugging numbers, we don't need those anymore. Plug in numbers. We have these two equations. But then again, too complicated. Some simplification is in order. We have to calculate all those and make it simpler. And I'd like to save some time. Please check. This -1 squared, so -1 and negative positive like this. And negative to the third power, another, so that's positive like that. All good? How about the next? Please check. -1 squared, so 1, and then negative positive, so +3. -2 times negative, so positive 4, and that's -6. Negative squared, so positive, 3 times 2 is 6, and that negative to the third power, so -1, so -2. All good? Okay, and then a bit further simplification. Oh, no, not that. That's not what I meant. Sorry again. Okay. So here, -1 plus 3, so +2. And then, yeah. Down here, -1 plus 3, so +2. All good? So I don't need this anymore. And compare this with that. Okay, let's solve. The first equation here has only one variable y, so solving that, it's not going to be too bad. It's going to be a quadratic equation, yes, but we have only constant and y squared and y to the fourth power. No cubic term, no linear term, so we can solve it. And the second one, well, we're going to consider the second equation a bit later. So there you go. Break up this complete square, and we get this. And then some simplification, 4 cancel out, subtract y squared, and that's what we get. Y to the fourth power plus 3y squared is equal to 0. And as a matter of fact, I showed you this a bit prematurely. Although simplification, yes. And then the key is to factor. Okay? This is nonlinear equation, higher order polynomial equation. So the key is to factor. Get the right hand side equal to 0 and factor. If I factor y squared out, when you get y squared plus 3 equal to 0, and right hand side is 0, so either one of them has to be 0. Y equals to 0, great. Y squared plus 3 is equal to 0, that's not possible. 3 is positive, and y squared is non-negative. So you can never get 0. Or y squared plus 3 is equal to 0. That means y squared is -3. Not possible. In any case, you're going to get y equal to 0. Make sense? So plug in y equal to 0 to this guy. Okay. This time, I'm not going to make the same mistake. Previously, I showed you the second line a bit prematurely. After doing that, I should have asked you a question. What do you do next? Should do factorization. Okay, all right, this time, okay. Let's plug in y equal to 0. So that's 0. So that's 0. Plug in 0. So 0 times something. So this entire thing is 0. Makes sense? Y is 0. 0 times 6. So that's 0. Y is 0. So 2 times 0 times something. 0. Make sense? So what do we have here? 2 times -2, so we get -8 equals to 0. That's the conclusion we get. So what does that mean? Please check the computation. You see, from here, plug in y equal to 0, and consequently negative 8 is equal to 0. Of course, that doesn't make much sense, but do you find any mistake? Well, no mistake, and I can tell you for a fact there's no mistake here. So what does that mean? That means this equation here is invalid. This entire equation is invalid. If it had been valid, this would have made sense. It doesn't. Negative 8 is never equal to 0, so this entire thing is invalid. But then again, what quantity here is causing the invalid thing? Y squared, 2, 6, those are all well-defined numbers. Problem, dy dt. The derivative is not defined. We do not have, the derivative does not exist, so this entire equation does not exist actually. And that's why we are seeing something like this. So the derivative does not exist. What do you mean by that? See, here I did the computation. The derivative does not exist. What do you mean by that? Well, here we go. Here's the implicit curve, and x is negative 1. Right here, turns out y equal to 0, yeah, right here. And what kind of tangent line do you see? You see, the derivative is tangent. What kind of tangent line do you see? It's vertical. You see, that's how everything is breaking down. This kind of thing can happen. As a matter of fact, sometimes things can break down for horizontal tangent as well for implicit differentiation, but let's not go too deeply into that. In any case, for implicit differentiation and related rates, sometimes something ridiculous can take place. That means that derivatives do not exist. All right, so much for those two example problems. We just went through a hard problem and a super hard problem. That's why I'm keeping those two videos, example 1 and example 2, both as optional videos. Okay, those are appropriate in Calculus 1, but in Applied Calculus, in 1325, yeah, I mean, theoretically they are included, and according to the catalog description, yes, I'm supposed to cover those, but in reality, I don't know. Who knows, you may have to take some standardized test and then it may show up there in whatever test you're taking, like AP exam or whatever I can think of. For that purpose, I covered, but only as an optional topic. The ball is now on your court. Whether you study those thoroughly or rather lightly or not at all, that's up to you based upon what your purpose is. Okay, so much for these two optional videos, and then we are going to go over to the next video, which is going to be required.